Hi everyone, welcome to part 4 of lecture 11. And in this part, we will discover or we will talk about the independence of the random variables. So the independence of a random variable from an event is similar to the independence of two events. So through the semester, we always talk about the independence and always we talk about the independence of the two events. So when we talk about that one, we say that a discrete random variable x is independent of an event A if the probability of X and A, so the verbal meaning of this, there's two guys will occur at the same time, which is equal to the probability of X times the probability of A, right? And we can show that the probability of X evaluated in some particular point times the probability of A, and that should be valid for every X. Okay, so any X values should satisfy this multiplication. So in other words, the events X and A are independent for all X. And the idea is similar. If two events are independent, that means the occurrence of the one of them will not provide any additional information about the other ones. Okay, they will not affect each other. So as long as the probability of A is strictly greater than 0 or strictly positive, the above condition is equivalent to the probability of X given A. So the conditional PMF of X is equal to unconditional PMF of X, because the idea is same. Even if there are some conditions that mean a piece of information is given to us, that information will not help us to get some extra information about the other events. That's why no matter there's a condition or not, the probability will not change. Okay. So the logic is same. We say two discrete random variables X and Y are independent if the joint probability mass function of them is equal to the product of the marginal PMF of them for all X and Y pair. Okay, so in other words, the events X and the Y are independent for all X and Y pairs. Again, as I said, the main logic is the same. A variable will not give some extra information about the another variables. Okay, they will not change the probability of other one. And the above condition, that one, is equivalent to the probability of X given Y is equal to the probability of X. Why? Because that conditioned event will not give any extra information about the X. That's why that conditional PMF will be equal to the PMF of X, unconditional PMF of X, okay? And that is for all X and Y, and such that the probability of Y is strictly positive. And also that rule can be extended for more than two random variables. So the logic is the same. If they are independent, if two random variables independent, that means they will not give any extra information about the others. That means the joint PMF of them will be equal to the product of the unconditional PMF of them. Okay, so that's the main logic. There are some useful properties. We can use them in many problems, such that if X and Y are independent discrete random variables, we have that the expected value of X times Y is equal to the expected value of X times expected value of Y. The proof is simple. Because I'm considering the expected value of X times Y, that means I have to calculate the summation of each pairs, the X times Y, so each pairs with the corresponding joint probabilities. Okay, so the expected value of X times Y is actually the two summation, one for the X and one for the Y, and I have to go over through all possible X and Y pairs. And remember that I have to multiply them with the corresponding probability. And because we have two random variables, we need to consider the joint PMF, okay? So I can split the summation because the X will not depends on the Y, okay? And also we know that the probability of X, the joint probability, joint PMF actually is equal to the product of the individual ones, right? So that's why I can rewrite this part. I can write this part as the probability of X times the probability of Y, right? So this guy and this guy is not depends on Y, so that they can go outside the summation, and I will get the first term. And then this guy will be the Y times the PMF of Y, the marginal PMF of Y. So this is an expected value of X, and this guy is the expected value of Y, okay? So that's why I can say that the expected value of X times Y is equal to expected value of X times expected value of Y if they are independent. So the random variables G of X and H of Y are also independent. They say the G is a function of X and the H is a function of Y. And if the X and Y are independent, we can say that the function of them are also independent. And also the expected value of G of X times the H of Y is equal to the expected value of G of X times the expected value H of Y. So remember that I just forget to mention, if they are not independent, you cannot apply this rule, okay? That is important. If they are not independent, you cannot apply that one. So expected value of X plus Y is equal to expected value of X plus expected value of Y, no matter they are independent or not, okay? That is not important. But for the multiplication, the independence is important. So that's why please notice that to apply this one, they have to be independent, okay? And for the variance, the variance of X plus Y is equal to the variance of X plus the variance of Y. If they are independent, we can apply this rule as well. Another one is if the linear combination of the random variables such that the AX plus BY plus C, and if I want to calculate the variance of them, I can just consider the coefficients of the X's and Y's. So I can calculate the A square times the variance of X plus the B square times variance of Y. Okay, so if they are independent, I can safely use these two the calculation methods. So these are the useful properties you can apply, and also these properties can be extended to several independent random variables. Okay, so they are easy. So, and also here, if they are not independent, you cannot apply this one. Okay, you cannot apply these two things. So please notice that these are valid for the independence, but this is not valid for the independence. It's not based on the independence, okay? Even if they are not independent, you can apply this one, but you cannot apply this one. If they are independent, you can apply this two and this as well. Okay, let's look at the continuous random variables. Actually, the things are very similar. We say two continuous random variables, X and Y, are independent if the joint PDF is equal to the product of the marginal PDF for any X and Y pairs, okay? And the idea is same. A continuous random, one of the continuous random variable will not give some extra information for other continuous random variables, okay? And that is equivalent to the conditional PDF of X will be equal to unconditional PDF of X, because that condition event will not give any extra information about the X, okay? So, and also these also can be extended for more than 2 random variables. So even if you have 5, 10, 11, no matter how many, but you can extend these properties for the more than 2 random variables. So let's get some useful properties again, and the idea actually same. So if the X and Y are independent continuous random variables, we still have the expected value of X times Y will be equal to the expected value of X times expected value of Y. So the differences is, instead of summation, I will use the integration, right? So to calculate the expected value of X times Y, what I need to do, I had to calculate the double integrate for the X and Y, and I need to integrate X times Y times the joint PDF, okay, with respect to Y and X. And I know that, I just seen that the joint PDF is equal to f of X times f of Y, the product of the marginal PDF, okay? So this guy is f of XX times f of Y, right? So for the first integration, this X and this guy is not depends on Y, so they cannot go outside the integration, and also dx. So this will create the first part, and the remaining will create the second part. And I know that is the X times the marginal PDF of X is the expected value of X, and the Y times the marginal PDF of Y is the expected value of Y. So that's why the expected value of X times Y, which is equal to expected value of X times expected value of Y. And also, if we have two functions, G and H, so G is the function of X and the H is function of Y, I can safely say that if X and Y is independent, G of X and H of Y are also independent. And also the expected value of product of that two function is equal to the product of the individual expectation. Okay, so the expected value of G of X times each H of Y will be equal to expected value of G of X times expected value of H of Y. And similar to discrete case, the variance of X plus Y will be equal to variance of X plus variance of Y. Okay. And the linear combination of that random variables, the variance of the linear combination of that random variables is same as the discrete one, which is the variance of AX plus BY plus C will be equal to the A squared times the variance of X plus B squared times variance of Y. So these are the same, okay? So only differences, instead of summation, we have just used the integration. And also these properties can be used for the several independent random variables, more than two, for the continuous random variables. Okay, so you can safely and easily extend these properties for the more than two continuous random variables. But how we can use that? I mean, how that can be useful? Suppose we are given a PMF of X and Y. So that table shows the joint PMF of X and Y. And the question is, are X and Y are Y independent? So how can we check that? Remember that the PMF, the joint PMF, which is equal to the P of X times the P of Y, right? But that should be valid for all X values, right? So the answer is no, because let's look at the probability of X is equal to 1. X is equal to 1, this one. So 1 over 20 plus 1 over 20 plus 1 over 20, it is 3 over 20. And the probability of Y is equal to 1, which is again 3 over 20. So the probability of X times the probability of x, the probability of y, should be equal to the probability of x and y, 1 and 1. But the probability of x and y, they are equal to 1, is 1 over 20. So they are not equal to this guy. The probability of x1 times probability of y1, which is equal to 9 over 400, is not equal to 1 over 20. That's why I can say that x and y are not independent. Okay, that's how we can use independence of two events in that way. And let's do the same thing for the continuous case. And suppose that the joint density of x and y is given with this formulation. The joint PDF of x and y pairs is the 6 times x times y times 2 minus x minus y for the x and y values, and x will be within this range between 0 and 1, and the y is also will be within this range between 0 and 1. So the question is same: are x and y independent? Okay, so how can I check that one? Well, so we know that f of x and y should be equal to f of x times f of y, right? So that's for each x and y, right? So I know that one. So to prove that one, to answer this question, I need to first calculate the f of x and f of y, right? So how can I find the marginal PDF of x? I will make x constant, and then I will change the y. I will evaluate the joint PDF for all possible y values while I am keeping constant the x, right? So, which is the f of x is equal to integration of the joint PDF of x and y with respect to dy. So I know that one that is given in the question, which is 6 times x times y times 2 minus x minus y and dy. So if I integrate these guys with respect to y, so I will get like, so that this part is 12xy minus 6x squared y and minus 6 times x times y squared, right? So I can get the integration of each parts here. So the first part will be 6 times x times y squared, and that will be evaluated for the 1 and 0, and minus 2 times x squared times y squared, and that will be evaluated at 1 and 0, and minus 2 times x times y cubed, and that will be evaluated again in 1 and 0. So if you make some simple math here, you will get the 6x minus 3x squared minus 2x, and that is 4x minus 3x squared. So that is the marginal PDF of x. So I will do the same thing for the marginal PDF of y, and in this time, I need to evaluate the joint PDF. I need to integrate the joint PDF with respect to the dx. So the y will be constant, and I will integrate the joint PDF for all possible x values. So I will do the same thing here. So I will skip them. That's the simple integration here. And at the end, I will get the 4y minus 3y squared. So I know the f of x. I just calculated here. And also I know the f of y. So the product of them should be equal to what? The f of x and y, and that is given to me here. The product of these guys should be equal to this guy, this one. So the product of them, the product of the f of x and f of y, so that should be y, okay? So f of x and f of y is equal to 4x minus 3x squared times 4y minus 3y squared, which is equal to this guy, and this guy is not equal to this one for all possible x and y pair. That's why we cannot say that X and Y is independent. So X and Y are not independent because they don't satisfy these equalities for any pair of X and Y. Okay, so that is how we can use the independence, how we can check the independence of two random variables. Okay, so that is the end of part 4, and I will see you in next part.